Hello, welcome to the New Zealand Cyber Operations and Risk Management Briefing. This briefing's intended audience is the New Zealand Chief Information Security Officer, selected cybersecurity officials, Five Eyes allied intelligence partners, as well as other interested stakeholders. Its goal is to present the security challenges New Zealand recently had to address related to our software assurance and our software development lifecycle programs. New Zealand recently was a victim of a ransomware attack that crippled operations and compromised some critical software deployments. This infection compromised several sensitive files and threatened possible legal prosecution, including the threat of arrest by the FBI. In direct response to this incident, the New Zealand Chief Information Security Officer swiftly ordered a whole range of investigations and reports to determine the scope of the infiltration. The focus of this briefing is directly related to the integrity of New Zealand's software insurance and software development lifecycle programs. A written report has already been submitted to the CISO and other Five Eyes security leaders. Software assurance is a discipline created in order to address software vulnerabilities, as well as to embed secure coding practices within the software development lifecycle. This is necessary due to the high-stakes pressure placed on developers to get new software to market as soon as possible. This creates a perverse incentive to cut corners related to ensuring software development secure coding practices. New Zealand does not, at the moment, have a mature software assurance program. It is recommended that the CISO endorse such a program to help to formalize the process for continued software maturity and process confidence. This is critical not just for New Zealand, but also for the allies we share information with and consume intelligence from. It is important for the state of these relationships that there is confidence in New Zealand's software assurance program. This can be achieved chiefly by making sure all software undergoes application threat profiles before being put into production as a final check on the exposed attack surface of the application. The software development lifecycle is an incremental approach to developing software in a controlled and manageable fashion. It is broken into various discrete steps in order to enhance quality assurance throughout the process. Each step's output serves as the subsequent step's input in a continuous loop of innovation and validation. Along with each discrete step, it is vital to not lose sight of how to incorporate security visibility and cyber operations into the process. Mature software development lifecycles attempt to incorporate security into and in between each step in order to ensure baked-in security that's inherent to the application. There are several versions of the software development lifecycle. New Zealand adopts the 5-step software development lifecycle version. The comprising phases include Step 1, requirement analysis, Step 2, design, Step 3, implementation, Step 4, testing, and Step 5, evolution and maintenance. Step 1 is requirements analysis. This step is the first and most critical to the success of the entire software development lifecycle process, as its outcome is the foundation for the rest of the process. The objective of requirements analysis is to gather the main stakeholders that have the need for the software, along with senior designers, to analyze and finalize system requirements. This is necessary to prevent scope creep, creating a situation where the project will never be complete as the requirements continually change. Outlining the system requirements up front in a concrete and succinct fashion helps define the boundaries of the project, defining mission success, which is beneficial to milestone achievements. Often, this phase involves answering a number of questions related to the goals and intended purposes for the application. The questions often are some version of: who is the intended audience for the software? How is the system intended or required to be utilized? Will there be user input? Will there be system output? And are there any system security or other compliance specifications? Step 2 is design. This step may or may not have holdovers from the previous step, most likely the senior designers, if any, but is mostly comprised of subject matter experts in the type of application outlined by the requirements analysis or the programming language dictated by the specifications of the application. The goal of this phase is to assess the outcome of the previous phase and develop technical specifications and designs that the next phase can use for actual implementation. Often the individuals that are in the design phase are team leaders and are devising ways to design the application according to the skill sets and strengths of their team members. The design phase may encompass both software and physical requirements, such as the CPU and RAM requirements for optimal software operations. It may also be determined that Python is a better language than C++ due to the team's familiarity, open source origins, and interpreted non-compiling nature. Step 3 is implementation. This is a step where the rubber meets the road, so to speak, and depending on the scope of the project, it may prove to be the longest phase of the entire software development lifecycle, as this is the step where the actual coding and development takes place. It is typical for teams to deconstruct large application designs into smaller units or modules for easier task delegation. Each team then takes their assigned module for isolated development. After each module is completed, it then undergoes some sort of integration testing as it is merged back into the main code branch of the application to ensure it does not destabilize the software once integrated. This integration testing is small in scope, however, as there is a separate software development lifecycle step devoted to more robust and functional testing, which is the next step. Step 4 is testing. The testing step, as its name implies, is completely devoted to the wholesale testing and validation of the software. In this step, functional tests are performed in order to ensure the end product meets the outlined customer requirements and security specifications. These tests may be intrusive and intensive in scope, as the goal is to verify that the application fulfills its intended purpose without causing security violations of either customer information or nation-state proprietary data. To achieve this, more robust integration testing is performed, as well as full system functional tests. Depending on the involvement of the customer in the process, there may be some user acceptance testing as well. In every testing phase, in every software development lifecycle program, there should be system security testing as well, such as input validation and bounds checking, as a final confirmation that the system was coded with security in mind. Contingent on the results of the testing, there may be an iterative feedback loop between this phase and the implementation phase in order to address any identified security or functional issues in the software. Step 5 is evolution and maintenance. This step serves as the production push phase of the software development lifecycle, making the end product available to the customer and end user population. In projects where the customer is not involved in the actual development, this may serve as the user's first chance to assess the software. Some implementations choose to use this phase as the beta testing phase, as a sort of post-testing verification step. The hope is that the user community or final customer accepts the application, which will effectively complete the software development lifecycle, after which the software officially enters a maintenance phase. If there is a different team that performs operations and maintenance that is separate from the design and build team, then at this point the software would transition to O&M. In the future, if there are any additional desired feature sets or security modifications needed, then the software would have to enter the software development lifecycle again, but this time the process would be streamlined. Within the software development lifecycle, there are different models of implementing the lifecycle. New Zealand has the following 3 models in operation currently: the waterfall, the iterative, and the V model. Models have different emphasis and objectives, as they are purposed for specific corporate cultures, project timelines, or subject matter expertise. Some models, such as the iterative model, are dedicated to rapid feature development in an iterative, continuous loop fashion, while others are more methodical, such as the waterfall and V method, in their approach, seeking a greater balance between quality assurance and security specification adherence. Regardless of the model chosen, all should have a defined end goal of marrying cybersecurity principles with software development guidelines in order to develop the safest and most functional application possible within defined time constraints. The waterfall model is a popular model within the software development lifecycle framework. Its popularity is due to its intuitive design and easy execution. Each step within the model cascades into the next, resembling a waterfall, in a sequential flow to ensure one step does not start until the previous step is completed. This model is most applicable to smaller projects or ones that have well-defined milestones and success indicators, and that is simple to track within the waterfall model. It is compatible with most continuous monitoring cyber operations requirements, as it allows easy assessments in a non-volatile environment due to the distinct beginning and ending stages of each step. Security assessments can be conducted at each step initiation and each step succession in order to bake in security to each phase as the project is in development. The iterative model is a reimagining of the implementation and testing phases into a rapid response feedback loop. At the end of each testing run, if there are any identified modifications required, the model re-engages the implementation phase to make those adjustments before re-entering the testing phase again. Implementation is broken into smaller sub-modules for faster feedback on each unit making up the software. This allows for rapid responses to small issues identified in small pieces of the application, instead of waiting until the end product and having to address multiple compounded design flaws. This model is ideal for cultures that value speed to market and fast turnaround times, often at the expense of well-defined requirements. This model also presents a substantial challenge to cyber operations, as its iterations may progress too quickly for thorough assessments and security validation. The V model is an extension of the waterfall model and one that emphasizes verification and validation between each step. The objective of this model is to add additional layers of security and quality assurance natively into each step. This is done by grafting and testing and assessment phases between each successive step in the software development lifecycle. Due to its regimented nature, this model is not quite as intuitive as the waterfall model and much slower than the iterative model. However, it makes up for these disadvantages in the benefits it produces to cybersecurity transparency within the lifecycle and enhanced quality assurance. Often, applications that are products of the V model arrive to market behind faster deployment models, but with far fewer security vulnerabilities and full functionality as required by initial requirements. In conclusion, New Zealand was susceptible and ultimately a victim of ransomware attacks due to our insufficient software assurance practices. In fact, comprehensive surveys and reports conducted after the compromise indicated that if New Zealand adhered more to mature software development lifecycle processes, this would have greatly reduced the likelihood of a successful ransomware infection, if not eliminated it altogether. It is this team's professional recommendation that New Zealand adopt the V model for all software development projects. This is to ensure consistent security approaches for every application in development. The end goal of this briefing and the recommendations of the written report is to be better stewards of our allies' data for continued collaboration amongst the Five Eyes nations. Implementing these recommendations will greatly enhance New Zealand's capability to participate in future Five Eyes summits with confidence in our ability to safeguard both our and our allies' data. Thanks for your attention to this cyber operations and risk management briefing for New Zealand. We hope it was informative and insightful. For additional and more in-depth information pertaining to this analysis, please refer to the submitted written report. Thanks again, and stay safe.